Okay, now we want to talk about inertia. And there are two kinds of inertia, linear inertia and then rotational inertia. So in order to explain rotational inertia, let's go back and review what was linear inertia. So linear inertia was the mass of an object. And then the official metric unit for mass was going to be the kilogram. So what did it mean to say that it had a certain amount of linear inertia? So imagine that you've got two boxes. So you got an empty box here, and then you got a refrigerator over here. And so you should notice that it's really easy to push on that little box and to get it to move. So let's say it's on ice, and you kick the box, and the box starts moving across the ice. So it's really easy to get it to move, okay? But then it's also really easy to stop it because you can run in front of it and stop the box from moving just with your hand. No big deal. But now let's look at the refrigerator. So with the refrigerator, now it's still on ice, and you're going to push on it, and it takes a lot of force to get that thing moving. Now, once it is moving across the ice, it also is going to take a lot of effort to stop it from moving. Okay, so the larger the linear moment of inertia, the harder it's going to be to get something to move linearly, and then the harder it's going to be to stop it from moving. So what is the analog when it comes to things that are rotating? Well, that is going to be called the rotational inertia. Another name is the moment of inertia, and it's given by the letter I. And then its formula, so I is going to be equal to a constant times its mass times its radius squared. So notice that both of these involve mass. Okay, so that if you've got two tires and the two tires have an identical radius, but the difference is one of the tires is a lot more massive than the other one, and you go to push on it to get those tires to rotate, you'll find that the one that has the most mass is going to be the hardest one to get to rotate. And then once it is rotating, it's also going to be very hard to stop it from rotating. So it depends on mass. But notice that rotational motion also depends on R. So do you remember when we talked about the connector between this and this, and this and this, and this and this was radius? So notice the connector between rotational inertia and linear inertia is, again, the radius. But notice this time it's radius squared. Okay, so it's also going to depend on the radius. So we could do an example of where you've got two objects that have different radiuses. And you would find that the one that has the larger radius is going to be the one that's going to be harder to get to spin. And then you also have the C thing. Okay, this is a number. So it's like 1, 2, 1/2. So it's always going to be some number that comes in front of the M and the R squared. So this is going to take into account the shape. So is it going to be a sphere, or in this case it's more like a cylinder that you're going to roll? Is it going to be like a bowling ball where it's a sphere, or is it going to be like a plate like this? So is it going to be something that like this that has a length and a width? So it depends on the shape of the object. it's also going to depend on where the mass is. So is the mass uniformly distributed inside of this, or is it hollow? And then it also is going to depend on how you rotate it. So are you going to rotate it like this, or are you going to rotate it like this, or maybe you're going to rotate it like that? So as you can see, rotational inertia is complicated. So what do I want you to know? The concept. So what do I mean when I say that something has a certain rotational inertia? It means it's going to be hard to get it to spin, and then once it is spinning, it's going to be hard to stop it from spinning. So as an example, the first one there, you've got different kinds of balls, and they're all the same radius, they're all the same shape, they all have the mass equally distributed inside the ball, but the difference is their mass. So you got like a lead ball, a copper ball, a steel ball, and they each have their own mass. So in that case, these two things would be identical, but whichever of those balls has the largest mass, that would be the hardest one to get it to spin. Okay, what about the second picture? So the second picture shows two balls. They both have the same mass. They're both balls, but the difference this time is their radiuses. So the one that has the larger radius would be the harder one to get it to spin. Okay, the third picture shows two objects. One is going to be a ring, and then the other one is going to be a disc. And you notice they both have the same radius. They're both designed so they have the same mass. The difference is the mass is at the edge of this one, and the mass is uniformly distributed in that one. So they're going to have different moments of inertia. And then the last picture there shows an object that's being spun like this versus an object that's being spun like this. So it depends on how do you spin it. And all of that stuff is inside of this formula. Now, here are some different shaped objects, and don't worry about them, okay? You're not going to have to know these shapes for the exam, and you're not going to need to know what their moments of inertia are. But if you were to take upper level physics, and if you knew some calculus, you would be able to mathematically calculate each of the moments of inertia for each of those different objects. So the moments of inertia are given for each one of them. You might need to blow up the picture so that you can see it. But you should be able to just barely make out the moments of inertia for each of those different shapes. You should notice that every one of the shapes has an M, and every one of the shapes has something squared. What's different about the different objects there is the number that is in front of the M. And that's what's determining the moment of inertia for each of those different objects. So here's a sample question. You have two wheels. So wheel number 1 and wheel number 2 have the same mass. But wheel number 2 has twice the radius. How do their moments of inertia compare? Okay, so remember, take the R and square it. So that wheel number 2 has 2 times the radius, so 2 squared is 4. So therefore, it's going to have 4 times the moment of inertia. Let's try this one. A solid sphere and a solid cylinder have the same radius and the same mass. Okay, part A, which one has the larger rotational inertia? So which one has the larger I? So we look up on this page here, so we go back to here, and we look up for the cylinder and the solid sphere and the solid cylinder, and we find out what is their moments of inertia. So one of them is 2/5 mr squared, but the other one is 1/2 mr squared. Okay, since they both have the same mass and the same radius, the only thing that's different about the two is the number that is in front of the m. So the cylinder has the larger fraction, and hence it will have the larger rotational inertia. Okay, which one would be easier to get spinning? So it's going to be the object with the smaller rotational inertia. And so that happens to be the sphere. Okay, let's take a break. Now we want to talk about what gets something to rotate in the first place. So I'll see you in just a moment.